Welcome to the Deep Dive. You've shared some really interesting stuff with us, articles, notes, all focused on something we all wrestle with daily, understanding and actually using instructions.
Yeah.
Think about it, from putting together that bookshelf that came in a million pieces
Don't remind me.
to finally mastering that tricky recipe or even just figuring out a new app on your phone. It's everywhere.
It really is. And in this deep dive, our goal is to pull out the truly useful bits from all that information you sent. We want to give you a clearer picture of why sometimes instructions click and, other times they just leave you scratching your head. We're talking about everything from those dense manuals that seem to be written in code to maps and diagrams that should be straightforward, but sometimes, aren't.
Exactly. And the key thing to remember, I think, is that it's not just about reading the words or looking at the pictures. The real moment of truth is when you try to turn that information into action.
Right. That's the crux of it.
That's where things either flow smoothly or you end up with, extra parts and a feeling of mild panic.
In there.
So our mission today is to really dig into how that translation happens and what we can learn to, make it work better for you.
Okay. So to really understand what's going on when we're trying to follow instructions, there's a helpful way of looking at it. Researchers like Guthrie, Bennett, and Weber came up with a model that looks at the main mental steps involved.
Okay.
They suggest there are 4 key things your brain is doing when you're trying to use a procedural document effectively.
Okay, 4 key things. Let's dive into the first one. They call it forming a conceptual model. Now that sounds a bit technical,
It does.
but what does it actually mean for you and me when we're staring at a set of instructions?
Well, think of it like this. Before you even get to step 1, your brain is trying to build a mental outline, a framework of what you're trying to achieve, and maybe even the overall process. It's like having a rough idea of the finished puzzle before you start fitting the pieces together. The work of Donald Norman really highlights this. Have you ever tried to use a door or a window where you instinctively push when you should pull, or you expect it to slide when it actually swings open?
Oh, absolutely, all the time.
That frustration comes from your mental model of how it should work being wrong.
That's totally relatable. It's like when you're trying to navigate a new website and you just can't find the button you're looking for because your mental map of where it should be is completely off.
Exactly.
So it's about getting that initial sense of the destination before you even look at the directions. Now, the research also mentions different kinds of these mental outlines, right? Something about understanding the end result versus understanding the steps.
Exactly. There are 2 main types. The first is the outcome schema. That's your understanding of what the final thing will look like or what will happen when you successfully complete the task.
Okay, the goal.
Right. The second is the procedural schema. That's your mental sketch of the sequence of actions you'll need to take to get there.
Okay, so if you're putting together a flat pack table, the outcome schema is the picture on the box of the finished table. And the procedural schema might be your initial thoughts like, okay, I'll probably have to attach the legs first, then the tabletop, something like that.
Precisely. And this is where some interesting research comes in. Dixon found that we tend to process instructions more easily when we understand the goal or the outcome first.
Ah, okay.
He looked at how people understood instructions like, turn the left knob when the alpha meter reads 20, compared to when the alpha meter reads 20, turn the left knob. People understood the first one faster. It's like our brains want to know why we're doing something before we focus on the specifics of when to do it.
That's a fascinating little insight for you. When you're explaining something to someone or even writing a to-do list for yourself, maybe try leading with the result you want to achieve before you jump into the how.
Yeah, it seems to help.
It seems to align with how our brains naturally take in information. And it wasn't just about actions, right? Dixon also looked at how we understand instructions about objects.
Yes, he found a similar pattern. Instructions like, to turn light Y on, press button B, were easier to grasp than press button B to turn light Y on.
Right.
Again, the desired outcome, the light turning on, provides that initial anchor for understanding the instruction.
Okay, so really trying to visualize the end result seems to be a crucial first step for you before you even get lost in the details. But what about the actual steps? That's where that procedural schema, your mental outline of the process comes in. How important is it to have that higher level view of what you need to do?
Smith and Goodman's research gives us some clues here. They looked at assembly instructions for a simple circuit. What they found was that when they gave people a higher level organizational guide, basically helping them build that procedural schema,
Right.
people could read the detailed instructions much faster and they made fewer mistakes. So instead of just saying, screw a nut on this bolt, they gave a broader instruction like, next, you'll be installing 2 more bolts that will connect with the battery. That little bit of context about the overall structure made a big difference in how well people could follow the detailed steps.
It's like getting the table of contents of a book before you try to read each individual sentence.
Yeah,
You have a sense of where things are going,
exactly.
and Holt and his colleagues found something similar when they looked at people using a word processing manual, didn't they?
They did. Their work showed that when people had a global understanding and overview of the main parts of the software and how they all fit together, they were much better at solving problems than if they just had a list of detailed instructions. Seeing the bigger picture of how the software was organized helped them navigate the specifics more effectively.
So the first key takeaway for you is, before you dive into the step-by-step, try to build a mental picture of what you're trying to accomplish and the general flow of how you'll get there. That an initial framework can really set you up for success. Now, the second key cognitive process is encoding procedures. What exactly happens in your brain during this stage?
Encoding procedures is basically about taking those individual actionable steps from the instructions and getting them into your memory so you can then perform them.
Okay?
And this is where things can often get challenging for you, especially with verbal instructions.
Because our short-term memory can only hold so much information at once, right?
Exactly.
Glover and his team actually looked at this with instructions for operating a printer, and the results were pretty eye-opening, weren't they?
They were. They found that people could only remember less than half of the steps for using a fairly basic daisy wheel printer right after reading them.
Wow, less than half.
Yeah. That really shows how much our memory can be a bottleneck when we're trying to follow even seemingly simple instructions.
Which probably explains why you rarely see someone trying to memorize an entire instruction manual before they even start.
Right, you just can't.
Instead, we tend to do this thing called iteration, right? We read one step, try to do it, and then go back and read the next one.
Exactly. Because our working memory has its limits, this step-by-step approach, taking in a small piece of information, acting on it, and then going back for the next piece is a really common and, well, often necessary way we deal with instructions.
Makes sense.
However, for some tasks, the order of those steps is absolutely critical. Think about putting together flat pack furniture, like you said, or following a recipe for a delicate dish like a souffle.
Right, can't mess up the order there.
If you get the sequence wrong, the whole thing can fall apart, literally or figuratively.
So for those kinds of tasks where the order matters, being able to recall the steps in the right sequence is super important for you. Now, research has also looked at how the way we learn, maybe even learning with someone else, can affect how well we remember these steps, right? Like that study about pairs assembling medical equipment.
Yes, O'Donnell and his colleagues found something really interesting. When pairs of students worked together to assemble medical equipment using a method they called distributed encoding,
Okay.
where they took turns reading and figuring out sections of the instructions and then gave each other feedback as they were doing it, they were actually more successful than pairs who just read the entire set of instructions first and planned everything out together.
Huh. So actively doing it in chunks worked better.
It seemed to, yeah. It really highlights how breaking down a complex task and actively engaging with the information in smaller chunks can be more effective for you.
That's fascinating. So it's not just about your individual memory. How you interact with the instructions and even with someone else can make a big difference in how well you remember and execute those steps.
Definitely.
Now, we've been talking a lot about written instructions, but procedural documents can also be visual, like maps or diagrams. How does this process of encoding work when you're dealing with those kinds of guides?
Well, with visual guides, the encoding process is a bit different for you. Instead of directly reading a list of steps, you have to actively figure out the steps by interpreting the visual information.
Ah, right.
Think about using a map to plan a route. The map doesn't say, turn left at the next light, then go straight for 2 blocks. You have to look at your starting point, your destination, and then mentally generate the sequence of turns and roads you need to take.
You build the steps yourself.
Exactly. The steps aren't written out. You have to create them yourself from the visual.
That makes sense. It's a much more active way of taking in the information. And the research has some interesting findings about whether people tend to prefer written or visual instructions, and when one might actually be more helpful for you than the other.
Absolutely. Lefebvre and Dixon found that when people were trying to solve problems involving geometric shapes, they much preferred having a visual example rather than just written instructions to figure out the procedure.
Okay, visual for shapes.
But on the other hand, Kovacs and his team discovered that for a task like driving in a city, written directions actually led to fewer wrong turns and got people to their destination faster than using a map.
Oh, interesting. So written was better for driving directions. Why the difference?
Well, the key seems to be this idea of transformation, how much mental effort it takes for you to convert the information in the document into the actual actions you need to perform.
Okay, the mental translation step.
Right. If the task is very visual or spatial, like understanding how shapes fit together or the layout of something, then seeing it visually in a diagram can be much more direct and require less mental translation. This fits with what Larkin and Simon found, that diagrams are really good at quickly and accurately conveying spatial information.
Ah, so with the geometric shapes, the visual example was already in a format that closely mirrored the problem itself, making it easier for you to understand the steps. But with driving, maybe the written directions provided a more direct, step-by-step guide that didn't require you to constantly interpret visual cues from a complex map. You weren't trying to, like, match the road signs to the tiny symbols on the map all the time.
Precisely. And Spangenberg's study on how people disassembled a machine gun really reinforces this. He found that dynamic visuals, a video of an expert doing it, were much more effective for you than static pictures.
Wow, like a video tutorial.
Yeah, the moving images showed the sequence of actions in a way that directly mapped onto what you needed to do physically. Similarly, Hayes and Hank's study on tying knots showed that pictures were far better than text for teaching that skill.
Makes sense. Tying knots is very visual.
Likely because tying a knot is a very visual, hands-on task, and the pictures reduced the need to translate verbal descriptions into a mental image of the rope.
That makes perfect sense for you.
Right, yeah.
So when it comes to taking in instructions, the most effective format really depends on what you're trying to do. And choosing a format that minimizes the mental gymnastics required to turn that information into action.
Okay, so we've talked about building that initial mental picture and then taking in the individual steps. What's the third key thing your brain is doing?
The third process is self-testing. This is where you actively monitor your progress as you're following the instructions.
Okay.
And you're comparing what you've done to some kind of standard, whether it's your own internal sense of what should be happening or an external reference like a picture in the instructions.
So it's not just going through the motions blindly. It's about constantly asking yourself, am I on the right track here? Does this look the way it's supposed to look?
Exactly. While you naturally do some level of self-monitoring when you're reading a book, to make sure you understand the general idea,
Sure.
self-testing in procedural tasks needs to be much more focused and happen more frequently. Think back to tying that knot. You can't just vaguely follow the steps. You need to constantly check if you've made the right loops and twists at each stage. Right, you need that constant feedback.
Yeah.
And the research suggests that the feedback you get, either from the instructions themselves or even from the thing you're working on, plays a really important role in this self-testing process for you.
Absolutely. Sunshmain argued that well-designed machines should give you clear feedback to help you test if you're using them correctly. If you press a button and expect a certain light to come on and it doesn't, that tells you something's wrong and prompts you to reevaluate what you've done.
Yeah, like an error message or
Yeah.
just nothing happening.
Exactly. And Glover's studies with the printer and the chemistry equipment are also interesting here. They found that while people who use memory tricks, mnemonics, could remember the verbal instructions better,
Okay.
both that group and a group who were just told to try and remember the instructions performed the actual tasks with similar accuracy, and both did better than people who had no directions at all.
So the memory tricks help recall, but not necessarily performance.
Right. It suggests that even if your memory of the exact steps isn't perfect, your ability to check your progress as you go your self-testing can make up for those gaps in recall. The thing you're working on, the equipment itself, can give you clues and information that help you stay on the right path.
So it's almost like the task itself and the tools you're using become part of this internal feedback loop, helping you confirm whether you're doing things correctly.
Precisely.
Now that leads us to the fourth and final cognitive process.
Yeah.
Self-correction. This sounds like what happens when your self-testing tells you that you've made a mistake.
That's exactly right. Self-correction is about recognizing when you've gone off course and then figuring out what you need to do to fix it.
Okay.
Surprisingly, even though we all have those moments of, oops, that's not right, when we're following instructions,
Many moments.
there hasn't been a huge amount of research specifically focused on this aspect of self-correction.
That's interesting, considering how often you probably have to backtrack and fix things when you're trying to assemble something or learn a new skill.
It is. But Petito's observations of math teachers helping students offers a bit of insight. The teachers would step in when a student made a mistake and guide them towards a more specific action to get back on the right track towards solving the problem.
Like providing a hint or pointing out the error.
Exactly. This suggests that procedural documents themselves could be designed in ways that better support your ability to self-correct.
How so?
Well, things like clear error messages, troubleshooting tips, or maybe very clear visual representations of what things should look like at each stage. All those can make it easier for you to spot and fix mistakes on your own.
So while there might not be a ton of specific research on self-correction itself, the idea is that instructions that help you identify and fix your own errors are ultimately going to lead to better results for you.
It seems logical, yeah.
Now, the model we've been talking about, conceptual model, encoding, self-testing, self-correction, really focuses on when you're coming to a task with not much prior experience. What role does your existing knowledge play in how you use procedural documents?
That's a really important point. The model by Guthrie and his colleagues is most relevant when you're tackling something new. If you already have a lot of experience with a similar task,
Like if you've built 10 IKEA bookshelves before.
exactly, then you're much more likely to rely on what you already know, your existing mental models and understanding of the process. In those situations, you might primarily use the instructions for self-testing and self-correction just to double-check that you're not missing anything, or maybe to troubleshoot if you run into an unexpected problem.
That totally explains that old saying, if all else fails, read the directions.
Right.
It's what you do when your existing know-how isn't quite enough or when you hit a roadblock.
Exactly. It highlights that how you interact with instructions isn't one size fits all. It really depends on how familiar you are with the task.
So this framework of building a mental understanding, taking in the steps, checking your progress, and fixing mistakes gives you a really helpful way to think about how you use instructions. How does this compare to other ideas about how we learn or solve problems? Are there other models out there?
That's a great question. The researchers specifically compared their model to Anderson's model of procedural learning, which talks about different stages you go through as you learn a skill, like declarative, knowledge compilation, procedural stages.
Okay.
However, Anderson's model is really about how you gradually become an expert at something over time through practice and
Like
refinement.
the learning process itself.
Yeah, whereas the model we've been discussing is more focused on that initial performance when you're actively using a set of instructions for maybe the first or second time.
So Anderson's model is about becoming a pro, while this one is more about getting through that first-time assembly or operation.
Precisely. They also mentioned Hayes and Simon's model for logical problem solving, like solving puzzles. While that model also looks at the steps involved in a process. The key difference here, the researchers argue, is that the model we've been exploring specifically looks at how your internal mental processes interact with the external information you're given in the instructions.
The link between the brain and the paper, so to speak.
Exactly. It argues that this back and forth between your brain and the document is crucial for getting things right the first time, which is something that models focused only on your internal thought processes don't fully capture.
So the big question then becomes, is this approach that looks at both what's going on in your head and the instructions themselves actually better at predicting how well you'll do when following directions compared to just looking at your thinking process alone?
That's the empirical question the researchers raised. They suggest that by understanding what kind of information in the instructions best supports each of those 4 mental steps we talked about.
Right.
An overview to help you build that initial mental picture, clear steps for you to take in, visuals perhaps to help you check your work, and ways to compare what you've done to the desired outcome so you can correct mistakes.
By understanding that interaction, we can get a much better handle on why some instructions are a breeze to follow and others feel like a total headache.
This has been so helpful. Okay, so just to quickly recap for you, the listener, the main things to keep in mind are, first, try to get a good mental picture of what you're trying to do before you get bogged down in the details. Build that conceptual model.
Yeah, get the big picture.
Second, pay attention to how the instructions are presented. Sometimes written steps are best, other times visuals will click better for you. Think about that transformation effort.
Match the format to the task.
Third, actively check your progress as you go. Don't just blindly follow the steps. Use self-testing.
Right. Monitor yourself.
And finally, remember that what you already know, your prior experience, plays a big role in how you approach and use instructions. You might skip steps or just use them for checking.
And the big picture really is that effectively using instructions isn't just about reading. It's this constant dynamic interaction between what's going on in your mind and the specific information you have in front of you. It's a dance between you and the document.
Well put.
So here's something to really chew on. Think back to the last time you really struggled with a set of instructions. Maybe it was assembling something, maybe following a complex workflow. Could you have approached it differently by consciously trying to build that mental model first? Were you really paying attention to how you were encoding the steps? Maybe trying to do too much at once?
Yeah, or maybe the format just wasn't right for the tasks.
Exactly. Were you actively checking your work as you went? Or did you only realize something was wrong way later?
Maybe even take a look at some instructions you have coming up for work, for a hobby, and see if they're designed in a way that supports these mental processes.
That's a fantastic point. Understanding these underlying cognitive mechanisms can not only make you better at following instructions, but maybe also at creating them for other people.
Absolutely. Thinking about how to help someone else build that model and code easily, test, and correct. Well, that's our deep dive for today. Thanks for joining us,
Thanks for tuning in.
and we'll catch you next time.